Hi, my name is Eliza Simondera, and this is my lab report for the third lab, Black Hole in Orbits. The purpose of this lab was to find the mass of a black hole with its net force, and to find an initial velocity for a spaceship to orbit both a moon and a planet. The concepts that were applied in this lab were Newton's second law of motion, which states that the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass, and gravitational force, which is the force exerted between two objects pulling them together. The equations used were the gravitational force formula, the velocity update formula, and the position update formula. The first part of this lab was to find the mass of a black hole. The system was a star with a trajectory unique to each person, and the surroundings were the black hole in space. This lab was done entirely in GlowScript. I first entered my Georgia Tech email, as this would determine my star's unique trajectory. I then added the mass of the star and the time interval, which was 1 day. In the calculation loop, I calculated the initial and final momentum vectors of the star with the momentum formula. I then calculated the star's change in velocity and change in momentum by subtracting the finals from the initials. I calculated dB dt by dividing the change in momentum by the change in time. I calculated p hat by dividing the initial momentum vector by its magnitude. I found d magnitude of p dt by finding the difference between the magnitude of the final position vector and the initial position vector. Finally, I found the parallel component of dB dt by multiplying these two values together. This is also equal to F-net's parallel component. Moving on to the perpendicular component, I subtracted the parallel component from dB dt. This is again equal to F-net's perpendicular component. I finally calculated the mass of the black hole by multiplying the magnitude of F-net by the magnitude of the distance between the star and origin squared, then dividing that value by the gravitational constant multiplied by the star's mass. After running the code, my star orbited the black hole and found its mass to be 1.04 times 10 to the 34 kilograms. The magenta arrow represents F-net's parallel component, and the cyan arrow represents F-net's perpendicular component. The second part of this lab found an initial velocity for a spaceship to orbit both a moon and planet. The system was a spaceship, and the surroundings were a moon, a planet, and space. Like part 1, this part was done entirely in GlowScript. In the calculation loop, I calculated the distance from the planet to the moon by subtracting their positions. I used this distance to calculate the force of the planet on the moon. This was found with the gravitational force formula, where I plugged in the planet and moon's masses and the distance from the planet to the moon. I did this again to find the force of the ship on the moon, the force of the planet on the ship, and the force of the moon on the ship. I combined the forces of the planet and the ship on the moon to find the net force on the moon, and the forces of the planet and moon on the ship to find the net force on the ship. I then used Newton's second law and position update formula to update the velocity and positions of the moon and ship. I also multiplied the original time by 10, resulting in 7,000 hours, or about 24.3 years. I did this so that the orbit could be better represented. I then used trial and error to plug in values for the initial velocity so that the spaceship would orbit both the moon and planet without running into either. I ended up with the x component of the initial velocity being negative 800 meters per second, and the y component of the initial velocity being 600 meters per second. This was the resulting orbit. Mathematically, the net forces, parallel and perpendicular components are the same as the rate of change of momentum's parallel and perpendicular components. However, the calculations and values required to compute these components are different. Net force requires all of the forces acting on the system, while the rate of change of momentum just requires velocity, mass, and time. In some circumstances, one may be easier to calculate than the other. If we wanted to predict the motion of a system with a black hole, a star, a planet, and a moon, we would need to calculate the gravitational force of each body in the system on all other bodies in the system, and find the net force acting on each body. This is similar to what we did in part 2 of this lab, but this would have more bodies and net forces to calculate. Because the black hole has the largest mass, it would be the dominant interaction. Thanks.